let's go ahead and get started. So I did want to spend about 10 minutes today talking about the project proposal. So this is an assignment that is available because I opened it up on Friday for you on Canvas. It's to be submitted with what will be your project group. So there's a little bit of a chicken and egg thing here. You have to read this and understand it, form your group, and then you can submit it. It is a 0-point assignment, the project proposal. So it's not worth anything. It is imperative, I think, that you treat it pretty seriously. You're being given a couple of weeks to write like less than 1 page, and I do want you to take the time to do that. So along those same lines, let me kind of walk through what my intention was of having this project and what I expect to see as the deliverable for the project proposal. So I mentioned this last week, but just to kind of reiterate, our projects, our conventional labs, are ending after Lab 8. So Lab 7 is finishing this week, and you're submitting it for next week, and then there's a 2-week lab for Lab number 8 on pointers, and then that's it. There's no Lab 9. So the concept is that you will finish Lab 7, finish Lab 8, start working on your projects, and that's what will take us through the remainder of the semester. In terms of the assumptions you can make for what you already know, well, we're a lot of the way there. I mean, we have basically covered all that one really needs to cover about structures. Pointers, I'm going to want to go slowly, but I think we'll cover it well enough that you'll feel comfortable using that as part of your projects. And then the other big thing is, how to use third-party libraries, right? Not necessarily how to make your own library like we were doing with the digital logic library, but how to use existing third-party libraries. I think that's just the case when doing programming in most programming languages and frameworks, and certainly for C programming. You can only do so much with your own code. You have to kind of build upon what others have already done. So most projects, I think, should start as some sort of a conceptual extension of an existing lab assignment, or make use of already existing libraries that we've already explored. So I wrote here that teams should be of size 3 or size 4, but our numbers make that a little bit tricky. So just to lay it out there, we have 10 students in the Tuesday section and 12 students in the Thursday section. So for the Thursday section, I want 3 groups of size 4 on Thursday. I've asked the TA to kind of nudge you to get that figured out just while you happen to be working on labs this Thursday. It doesn't have to be 2 groups that kind of smush together, but that also works too. So if you're working well and you see another group that's working well, feel free to get together and form your team of 4 and let the TA know who that team is. For the Tuesday lab section, we have 10 students, and I'd like it to be a 3, 3, and a 4 group. And for those teams that are 3, the scope can be somewhat less than those who are doing a team of size 4. But the programming complexity doesn't necessarily scale with team size either. It can be very hard to kind of split up the work amongst many people. If I said we could have one team of 22 students, I don't think that would make your job very easy, because figuring out how to partition the work and to set the scope appropriately is kind of tricky as the team gets larger. So my intention is not for those 2 teams of 3 that we will have to be at any disadvantage, and I don't think that will be the case. Another thing to take note of is, we won't have a final exam in our scheduled final exam slot, and I think you already knew that. We have one more macro quiz near the end of the semester, but no other no proper final exam. But we are going to use that final exam time slot, so don't book travel that involves skipping out that week in December. We're going to do our kind of final project kind of presentations where you're demoing off what everybody worked on to the entire class, and not just to me or to the TA. Another big gotcha is because the projects are going to be different in terms of what you are working on. For Lab 7, everyone's doing the same thing, so we have a fixed rubric. Same for every individual lab we've had. For the projects, that won't be the case. So for the projects, you are going to get to help design what your grading rubric is going to be. That's a good thing, in the sense that you get to define what success is, and you get to set your own goals and meet those own goals. That's also a challenge, because up front, before you've gotten really started in the project, you have to think it through. You have to think through what are the challenges going to be in the project, what major tasks are we as a team going to have to accomplish, because you're going to want to set your rubric accordingly. If I'm going to spend 50% of my time doing something on this project, then that should be worth roughly 50% of my score, so that your time matches the effort intended and the resulting grade that you get back out. So beyond those parameters of Tuesday teams, Thursday teams, the team size is kind of given as I mentioned here, you're kind of, up to doing anything you'd like to. Propose anything that kind of matches your group's interests. I have some potential project ideas. I can come up with many other potential project ideas if you're just completely stuck and you hate all these particular ideas. I'm also, very open to discussing project ideas with you before you formally propose it. That discussion could just be based on a one sentence, message posted in the projects channel in our class Discord, or come to my office hours and discuss. And I won't necessarily say good project, bad project. I don't think it's always ever that simple. It's more of, okay, think about this issue and this issue and this issue, and if you think about those issues, then this could be a good project. Or watch out for this pitfall, or this pitfall if you pick this other particular project. Don't overanalyze this table of potential project ideas. So I gave a sample title, a very high-level description of what the project could be, and then when I say relative difficulty of high, conceptual, and moderate program, I wrote that, I thought about it a little bit, but it depends. Conceptual difficulty really depends on what you're good at. Do I understand the math of this particular problem, or if there's an algorithm involved in it? Programming difficulty, I have a better feel, but it really depends on what in particular you are proposing and what tasks you set aside for yourself. So here's just some of the project ideas. So we did a barcode generator. Some really struggled with that one. Others kind of just dominated that example. QR code generator, it's a slightly more open-ended problem than a barcode generator, but you can think of it as kind of a two-dimensional version of the barcode generator problem. So with a libgd type library and copious reading of Wikipedia and similar links for how that gets generated, I do believe a team of 3 or 4 would be able to do a cool QR code generator. Connect 4 is something that I would think we could have had as just an individual lab. What I wanted for this project would be Connect 4 against an AI opponent, where AI is kind of a loaded term. But Connect 4 is a solved game in that there's perfect play possible, and there's algorithms for how the first player can always win in Connect 4. I hope that doesn't disappoint you to learn. So you should be able to implement something like that, an AI that can win every time against you in Connect 4. I mentioned here, and I may mention a couple times, this curses or ncurses console application. We haven't learned that yet. Lab-08 does involve using that curses library as like a separate learning outcome than learning about or using pointers. It's different than printf, but it's just another way to get text to display on the screen. It allows us to, as opposed to always just calling printf and going line by line by line, it allows us to put a character in a particular place on the screen. So that opens up some things that otherwise we probably could always do printf as an equivalent, but it'd be very painful. Curses, while it's a little bit more syntax, you'll see that it's pretty straightforward to draw things in particular ways and be a little bit more artistic with what we put in the console. Same for the Minesweeper. That's going to be a Lab-08 application. I really like Minesweeper as a programming exercise. If you find yourself really enjoying that part of Lab-08 and like having fun looking at the algorithm for it and how to make it better, that's a perfectly valid project as an extension of what we've already done. Sudoku kind of lends itself to a console-based implementation, so go for it. That's all good. Another one I didn't mention here is Wordle. You could do as well, where you have a word list and people are. That's a sufficiently scoped project. If you have a reasonably full-featured version of the same. Some sort of interactive video game using a game development library. This would be a graphical game versus just a console-based game that we're already doing for lab number 8. That could be fun. It may not be as fun to develop in the Replit environment. So before you propose that, I'd want you to confirm that you can get that library to work, that you can get little like application to pop up and it's not super laggy and painful to play around with. But conceptually, building a game using that kind of library isn't going to necessarily be any harder than doing something with a console application. You can write a Discord bot. There's a C and C++ library for interfacing with Discord. I'd want the bot to do something useful, but come up with something and have fun with that responds to every question about extension. Can I get an extension? When it sees the word extension on the homework, it just responds no to that question or something like that would be a very useful bot. You can build a chess engine interface. I wouldn't want you to try to build a chess engine yourself. I think that's a big leap. But there's existing chess engines like Stockfish, and can you interface them with a C program and maybe display the results of the analysis or of a game actually being played? Okay, I'm not going to walk through every single one of these, but that is about, 15 examples I have here for you to look at. You are not required to pick any of these. You're very also welcome to take one and kind of twist and change what it's going to be about and be just influenced by the idea, or you can just go completely outside the box and do something totally different than any of these ideas. The choice is yours. I'm happy to discuss the idea with yours. I will tell you though, we have this assignment worth 0 points for proposing the project. Once you have submitted it and once I've kind of checked off and said good, I may ask you to revise it, but if I said good to go, that is your project. You don't come to me the night before and saying, we've changed our mind, we've done a totally different project. You're gonna commit to that and I'm gonna commit to you working on that project. So I want you to think about it. So don't just throw out an idea and not think about it and say, hey, wouldn't it be great if we built such and such application for our project? I don't want you to do that. I want you to think about it carefully. Maybe even involve like minimal proof of concept. If you want to use a new library that you haven't used before, can you confirm on your own that you can actually get that library to work? And I can help you with that too, but can you actually do some of the groundwork to convince your team and yourself that, hey, this project is manageable. I will be able to get this project done. That's necessary because we have a little bit of time to work on these projects together, but we don't have months and months and months of time. So I want you to think about the scope associated with that. I say this down here at the bottom. This is a 10 to 20 part-time person week project, not a 2-semester capstone or a graduate thesis project. The temptation, I think, is that as you propose your project idea is to come up with something really, really impressive. And none of these fall into that category, but like something just really that would wow me and just kind of, just be incredible. I want you to resist that temptation, right? Just think about the amount of days, weeks, hours you have to work on this project. I want you to pick something that you can accomplish. And don't try to impress me with your project proposal. Try to come up with something that is feasible and doable, given your interests, given your experience, and given that for many of you, this is like your first real programming course. In terms of deliverables, I want us to try to form our teams this week in lab. So this says before the due date of this project proposal, send an email. I'd like us to work that out this week in lab if at all possible. There's only 10 in the one section and 12 in the other. We should be able to come up with our project teams. And then the submission is going to be this one-page PDF that describes your proposed project. So an overview, what are you hoping to accomplish? A list of project goals that have to be pretty specific. Like what does it mean to actually deliver on this project? That's going to be really specific to your individual project. What steps do you think you're going to have to accomplish? I want a very quick mock-up of what the potential end result would look like. That could be hand-drawn, that could be drawn in some like editing program, however you can provide that. I want a timeline, and this is a very short turnaround timeline. How are you going to be able to get this done to demo during our final exam week together as a class? How are you going to kind of try to split up the work? If everyone's going to work together, that's fine, but oftentimes you want to have subcomponents and have things kind of tied together at the very end. I guess those are all important. Especially I would guess B of those 4 things are the most important, the list of project goals, because then E is definitely the most important. That's the grading rubric. So this rubric I provide here, you are not to copy paste. You can start with this. This is a grading rubric for a project that would be like a library database program, like a university library, like a checking out books and keeping track of books in a library program. So we read these rubrics. They're kind of similar to the type of rubrics you may have seen in Canvas. We use rubrics to try to grade everything as a kind of a general grading philosophy. It's a table. On the rows are the individual attributes, and you can think of those as features of your projects, either actual features you want to implement or underlying implementation features themselves. So for example, I mentioned as an attribute for this example project that data structures. Here are the different data structures you're going to generate and how you're going to generate them to support the rest of the program. You're going to spend a lot of time doing that, right? With our blackjack example from Friday, thinking about the data structures first help to enable the rest of the functionality. Here then, additional attributes for this example are just the different components and features of the project, how you would initialize the library, how you would interact with the library, what the user interaction would be, what it would look like visually as well, with then a 5th attribute for project organization, where at a bare minimum you have a well-documented, organized project with a README. If there's some sort of clear final presentation and demo, you can give yourself full credit. If you have additional aspects of organization, you can potentially get bonus credit for that as well. So that is the rows here of this grading rubric. You should have 5 rows in your grading rubric. Then we have the columns for how well you did for those particular attributes of your project. The goal of your rubric, and you can copy paste the structure of this, is to have 3 different categories for which you may fall somewhere in that range. Just like how we're doing our grading in Canvas this semester. Beginning, meaning or unsatisfactory, or low level, you made some progress but didn't quite hit your actual goals there. Accomplished, which is our goal, you have hit what is required of that particular attribute. And then for all of these attributes, give yourself some stretch goals. If I did something beyond what the bare minimum I said I wanted to accomplish to have a successful project, I'm going to give myself bonus points for that criteria as well. So you can kind of see the structure of 5 attributes for a 200-point project. A full score on this, an A on this project is 200 points. So you have 5 attributes. Each of those should then be 40. Our blue highlighted column here is 40 points for each of those individual attributes. That is a fully successful project with potential for potentially more if, in fact, you do something beyond and above and beyond for one of those individual attributes. This part is the most important part of your project proposal. I'll push back if I don't like something about it. Usually the kind of thing I would push back about is if it's really vague. I want to be able to grade this. I want you to be able to do a self-assessment as well, and it should be really clear what it means to get 20 points for something, or 40 points for something, or 60 points for something. So as you work on this, avoid ambiguity, avoid vague terms like, does a good job initializing this library? I mean, what does that even mean, right? And it's impossible for me to evaluate that. It's very hard for you to self-evaluate that as well. Think of it in terms of tangible things. I believe that'll take you some time as a team to come up with that and agree on that. And it may involve a little bit of exploratory coding to see what is feasible, what would require extra effort and maybe should be pushed into exemplary, that 3rd category here for performance and proficiency scale, what can fall into kind of the middle, the expected, the accomplished, satisfactory, medium level scale here. I expect those to fill out this entry of tables. That's just 15 entries here. I expect that to take your team a solid week of discussion, either in person or online, to come to some consensus about what is required for that. So you're going to have 5 total attributes, set the goals in such a way that satisfactory adds up to 200 points. If you really are unsatisfactory, maybe that would lead up to 100 points. And if you could have an exemplary project, you could potentially get up to the 300-point range. So this is definitely an opportunity if you've been maybe missing some points here or there and really do care about your final grade in the course. A 200 is certainly an A on this project, but you have the opportunity to kind of make up for lab points that you may have lost, early in the semester with your team here. This final point here, and I kind of was getting at this already, successful projects will be those that have a solid plan, and oftentimes a solid plan requires some initial exploratory work. It's great to just throw out ideas. I think, that ideation phase where you're just discussing different ideas and writing down notes of potential ideas, that's a great necessary step. As you start to kind of firm up what you're actually settling on, it's worth it to confirm feasibility of those individual ideas. It's a little bit of a chicken and egg. You can't do the project to determine if the project's doable, but for individual components, are you proposing something that's feasible? How many hours do you think it would take and why? It may require some exploratory work. This is why this assignment is not a 10-minute assignment. You have 2 weeks to work on this assignment, and it's worth 0 points. But it directly influences those 200 points you're potentially getting, for the end of the semester assignment. That was a lot of me talking. This is all recorded. You can review it later. Any questions about your project? Okay. Start to think about your teams and what would be appropriate for your team. And let's start to get organized now. Your submission for this will be on a team-by-team basis. So that's, as I mentioned, that's 3 teams on Tuesday and 3 teams on Thursday. So I should see 6 submissions for this. I mentioned here somewhere, your final presentation is going to be like an 8-minute presentation. That's actually kind of hard to do. You're going to want to talk a lot about your project. With only 6 projects and we have 2 hours together during the final exam slot, we can do more than 8 minutes. I'll figure out the exact right format for that when we get closer to that date, but you'll have more time to discuss your projects. We will probably also spend time in class after this deadline discussing the projects as a whole class so you get a feel for what everybody else is working on. I don't want any 2 teams doing the same project, so you can use that projects channel to kind of reserve a concept. Even if 2 groups really want to do something very similar, I'm sure there's ways we can kind of separate the concept so that maybe 2 teams really love Minesweeper, but you can focus on some different aspect of Minesweeper and I think still have room for 2 teams to work independently on their projects. Questions? Comments? Concerns? Yeah. I know you showed up late, so you can review the video for that. These are starter ideas, and you can certainly take one of those or propose your own based on these. These were all projects I thought were doable. That was why I picked those. That if you have no idea as a team and just can't settle on something, pick one of those. You still have to do the work. So even if you're saying I'm going to do a processor emulator, you took CPRE 281, you really loved it, you found that lab easy because you've taken that class and you know that stuff, and now you can build like a working, a simple processor that can run some assembly programs. That's fine, that's an idea. You still have to go through the process of what your rubric and deliverables and all that are going to be. So picking one of those doesn't solve the problem, but it gives you a starting point as a team to come up with that particular solution. Okay. Hey, don't stress about it. It's meant to be kind of an end of semester celebration at the end of the day. And if you create your rubric well and you're kind of intellectually honest as you're working on the rubric and you avoid kind of vague terms and ambiguities, you're going to get a good score on this. At least in past experience, that has been the case. That our average on this project has been over 200 points out of 200, and it's been good for everybody's grade. It's not been bad for everybody's grade. The downside of working on a project versus a lab is, the kind of help you'll be able to get from a TA or from myself will be a little bit less specific usually, right? Like, for Lab 7, you're stuck on something, you come to my office hours, I tell you what I want you to do for that part of Lab 7. For your project, it's kind of up to your team, right? If you're stuck on a syntax error, I can still help you. If your code's crashing, I can still help you debug it. But otherwise, you're kind of on your own in that sense, right? The TA can't tell you what to do for that project. We can always make suggestions, but it's kind of up to your team. So that kind of aspect makes it a little bit scarier than just doing another lab assignment. But I think it's hopefully a lot more kind of, freeing as well, that you're not limited by what I tell you to do. You get to decide what you're doing for that particular project. Okay, so that then involves a pretty big switch of gears to our next lecture topic of pointers. I think some instructors will tell you that, pointers are the hardest part of C programming, and you won't understand pointers for several years. I guess with anything with programming, my philosophy is, you'll get some experience with it now. You'll learn enough to be able to use pointers in your programs. It just takes time. There's no quick fix for it. It's also not some completely non-understandable concept. I think, though, that for pointers to be something we can handle via 1 week in class together, it does require you to have pretty good footing for how we've gotten to this point. And so that I can't necessarily guarantee, but we'll walk through these aspects of it. So we'll start with some kind of lame conceptual analogies, as I want to do. We'll talk about specifically function arguments with pointers, which we've been doing a little bit of already. The pointer array equivalency is really just one slide, but I'm going to kind of repeat myself maybe 10 to 15 times because it's very critical that we understand that concept. And then dynamic memory allocation is where pointers get kind of messy. And we'll spend time, we'll learn how to do it. We'll go through some examples that I think, look very hard at the beginning, but by the time we're done with them, we can logically walk through what we have done. So I say congratulations, but no congratulations yet. You're still on Lab 7. So looking back at functions, part of our motivation for pointers, or part of our use case for pointers, was this kind of limitation that, we can have multiple inputs to our functions, but we're really limited by our, individual, function calls returning one thing at a time. We've talked about some of the, and I think we already understand that, we can use the function everywhere a value of that return type is expected. We have some other workarounds. The struct itself is a workaround for returning one thing from a function. We're still returning one scalar variable, but that structure can have all sorts of things inside it. That's useful when your data has structures, and that's probably the right approach for it. Our data doesn't always have structure. We also talked about arrays as a potential workaround. I want to return not just a single value for my function call, I want to return an array of values. Well, because of this array pointer equivalence that we will see, that also works for our purposes. We pass an array, the name of an array variable to a function. We can both read from that array. We can also update the values of that array inside that function. That's not a separate workaround than this, but syntactically it winds up looking a little bit different. This other approach of returning more than one thing per function call is something we've actually already been doing all semester, right? This syntax, right, of scanf, right? We call scanf, and depending on what we provide for that format string for scanf, we could potentially overwrite multiple variables in that individual function call, right? Scanf %d, 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 reads in 3 integers separated by spaces from our console, from our command prompt here, and updates 3 different variables with that typed in values. And for the most part, we said, well, just assume that that works and don't think about it too much. Well, let's talk about, that's what this topic is. Why does that work? How does that work? How are these variables working in this mechanism for us to be able to update multiple things in multiple different ways, including via a single function call? So this is our current view of memory, right? This is a slightly different view than what we've seen before, but we know that when we have these variables and these names of variables and these types of variables, it's an abstraction to kind of avoid having to look at memory as just this array of bytes. That's ultimately what our memory is in the computing systems we are working, an array of bytes that presumably starts at address 0 and goes to some very large address. And usually for these systems, it's a byte address, but that's an implementation detail, but that's reflected in the values we will see when we look at pointers here. So when we declare a variable int a, what is actually happening via the compiler is we're saying we want 4 bytes of memory. And 4 bytes of memory, the actual contents being whatever they are, they're going to then be interpreted back to each other as being a single 32-bit or 4-byte value that is going to hold this integer data type for that variable. And that's all that we have in memory. We declare variables, either single variables or arrays of variables or structures that include these variables, and we're allocating memory when we do so. The compiler is doing all that for us. We don't see it happening explicitly, but when we declare 2 integers, the compiler is finding 8 bytes of memory for us, and it's putting those variables at those locations in memory. A pointer is nothing more than a variable that is used to store an address in memory, which we can then use to indirectly refer to other variables. That is all a pointer is. I wish I should have put like flashing font or bold or different color or something like that. The rest is entirely syntax and implementation details. If you could kind of regurgitate and like have that be your pointer mantra, you'll never go that far afield when dealing with pointers. A pointer is nothing more than a variable type for storing an address in memory. All variables have an address. A pointer is a variable that stores an address. Pointer, address. Address, pointer. That's all they are. It's a variable whose value is itself an address, presumably for another variable, but it's just an address. It's some, like these byte addresses, a valid pointer here would be storing 0, 1, 2, 3, 4, 5, 6, or 7. Real memory is a lot uglier and messier than that. It's 32 or 64-bit values, but that is all that a pointer is. It is storing some address in memory of something else. This ampersand operator is one way we can indirectly refer to a variable's address, and you can actually print with %x, but %p is a format string specifically to print the actual value of a pointer. There's a little bit of syntax we haven't covered here yet, but when we declare int a and int b in our program, they are given addresses by the compiler. We usually don't really need to know what that address is. It's some value, and it's some value we can store as a pointer. And if we need to actually know what that address is, where did A and B actually get placed in memory, we can print it out. Address of A, and that's how you should read that ampersand symbol. Address of A, address of B. That's for A and B being regular integer variables. We use the ampersand operator to specify, not logical and anymore, unfortunately. It'd be nice. It's being having multiple uses here. Here it's being used as like the address operator. Give me the address of A and the address of B. We can also specify special types of variables that are called pointers that are themselves just being used not to store an actual value in memory, but an actual address of some other variable that's going to correspond to something in memory. That's the syntax for this here. Int star C, I don't know, int star pointer C, I don't know how you want to pronounce that. Int star, so you're being very clear that it's a pointer that you're declaring here. Let's ignore this line here. Let me actually uncomment out the other line. Let's ignore that line for now. That is a pointer variable. It's not meant to store an integer. It looks like it. This is the syntax that C gives us here. It is not meant to store an integer. It is meant to store a pointer to an integer, and that's how you should read that syntax. C is a pointer to an integer because it's got that star there. And this is one convention. It doesn't actually need to have like a lack of space. Space is irrelevant in C, right? So you could have done that or this or put it there. I don't know. There's different conventions. That's how I do it, so that's how I want you to do it. Int space star C. This is a pointer to an integer. It is not an integer. C does not store an integer. C stores an address. We have to put something in C for it to be a meaningful address because it's just like any other variable, it's not initialized at all. It has nothing until we initialize it. One thing we could store to it would be the address of some integer. C is going to be set as the address of A. We could then print out A, B, and C. Now, the issue of printing these out is they're just really long-looking kind of hex strings, but, so be it. That's how they're getting printed out here. They're put in that particular location in memory. There's no guarantee, and I think we've tried this a couple of times, that your answer for printing that out will be the same as my answer. It depends on what else is running in memory in that particular system. And in fact, when we run it twice, we get different results for where this program happened to get placed in memory. That's one of the reasons we tend not to care about the actual value of the pointer, meaning like what was the actual location in memory, but we have to use pointer to keep track of things in memory. We can occasionally print them out for debugging purposes, but they're in random places and they change each time. So we set A as just an int and B as an int, and we printed out the address of A and address to B. And then separately we said C itself is a pointer variable, and because we set C equal to the address of A, we get the same result when we print that versus when we're printing A. That is the syntax for how to print out our pointers. Our pointer is nothing more than a variable that stores an address in memory. I guess I could have shown that. Address of A points there, address of B points there. Here's a mediocre pointer analogy. This gets a little bit recursive, which is why this is a mediocre pointer analogy. Pointer is our key. The key specifies, remember our mailbox analogy, right, from like the first week of the semester? The key is our pointer. It specifies the location in our mailbox in memory where I can access mail or access my data. Here, the key itself is the pointer. Itself has a value of 333 here. That's the location in the mailbox. It's the location in memory where I can access data. You can use the key. It's called referencing the pointer, or following the pointer is the other term you will see used, like in your Zybook and in other resources, to open the mailbox at 333, to read the data at address 333. And then here's the actual data. Here's the mail in the mailbox in box 333, which you can then just take a look at. That would be reading it, or you can modify it. You can rip it up, or you can change what's in the mailbox and update the locations of those. It's a valid, but it's kind of just a mediocre pointer analogy. Part of the issue with this, and I don't want us to go too far in this kind of recursive direction, is, again, here's my definition that I wanted you to always have. A pointer is a variable that stores an address in memory. Pointer is a variable that stores an address of memory. The pointer itself is also a variable, right? I said that's part of the definition. Int AB is a variable. Int star C is also a variable. So if we really wanted to really complete this analogy fully, that variable itself, that key itself, would have to have been in the mailbox somewhere as well, right? So somebody has to get the address of where that key is stored. You then grab the key, detect that it's key for 333, then you open the mailbox at that point. So for that reason then, and you can and do have a pointer to a pointer. You can have a key to a box that contains a key to another mailbox. The issue is there's really no end to that. So oftentimes a pointer to a pointer is as far as we go in our programs. Address, if you can just think of that, you're fine. If you want to think of this key analogy, that's fine. We're not really unlocking and locking memory in that sense, and that's kind of the failure of this analogy here. But it stores as part of the variable where in the mailbox you're looking. Where in memory are you looking for that particular variable or other thing in memory? Here's a slightly better pointer analogy. Yar, here be me pirate treasure map. Okay, ahoy me pirate booty, right? So the mailbox memory analogy only goes so far. We don't really unlock memory. So the treasure map is a little bit closer to what we're talking about because we don't lock and unlock memory. The pointer tells us where we have something interesting potentially in memory. So it's a little bit closer to a map So instead of mailbox, if you think of your memory as being treasure that you have to find, that's fine as well. Maybe we're past the point of needing silly analogies to understand this. Our pointer stores our addresses in memory. Syntactically, why this is a little bit uglier than one would hope in a programming language. And one would say this is a downside of writing C code versus other languages that try to hide this abstraction away from you, is because our data types in C are different sizes, right? Potentially. Our ints are different than our chars, are different than whatever structs we may create on our own. The number of bytes each point or each variable has is different for those different types. Remember shorts and longs and things like that, not to mention our custom structures. For that reason, because our data is a different size, depending on the type, our pointers then are also going to be type specific. So it's not just a treasure map. It's not just a treasure map where X marks the spot. It also tells you how far you have to dig, I guess would be how, if we really want to continue that analogy. For our pointers to work correctly, or another way to say that, the pointer has to also just say, not that this is the starting location in memory where our variable can be found. It's how many bytes are in that starting at that location in memory where our variable can be found. That is data type specific. For ints, it's this location, and it's the first 4 bytes at that location. For longs, it's 8 bytes. So it's same starting location potentially, but it's the next 8 bytes. For your custom structure, it's whatever that size of operator returns for that custom structure that you yourself have created. So that is why syntactically, for better or for worse, when we're working with pointers in C, it's not as abstract of thing as maybe we would like. It's an address, but it's an address that's kind of coupled with a particular data type. So our syntax for that is very data type specific. Just like we would declare an arbitrary variable, we would use the data type of whatever that may be for our custom structure or int or whatnot, declare a variable of that type. When we then also would want to declare a pointer, that pointer is pointing to a variable of a particular type. So it's always data type star and then the name of our variable that is going to be our pointer. The 2 main things we then do with our pointers are we can set a pointer to a particular address. There's some function calls we will use to do this for certain reasons, or we use the ampersand operator to get the address of a particular variable. That's one thing we do with our pointers. The other thing we do with our pointers, and scanf does that as well, right? The other thing we do with our pointers is, and I use dereference and reference and follow the pointer. We open the mailbox, right? We are going to actually check what is in memory at that particular location. These slides say both reference and dereference. I don't actually know which one is correct. I think reference would be correct, right? We're referencing that location in memory. We're looking up what's in memory at that location. That is then that star operator being used again here. Let's go back to this. I say dereference again here. Well, anyway, it's so star to declare that something is a pointer. We then use star again when we want to follow that pointer. We want to do something with memory at that particular pointer's location here. So here we have AB. Let's initialize A to 2. And this is still going to print out the pointers, but we're just going to update this example here. We then have declared a variable. It's an int star. It's an int pointer. It points to an integer. We're setting to actually point to A via that ampersand operator, the address operator. C is at A's location. Right now, if I do A is, I don't know why I have to do that, A equals this, and I print out A, what's it going to print out? It'll print out A equals 2. There's no trick here yet. But because C is pointing to that same location in memory, C is a variable that stores, this long string of location, just a big location. It's somewhere in the upper ends of memory. It's on our stack. We've talked about that a little bit. So it's up there in memory near the top of memory. If I now choose to follow the pointer, I think it's reference. I keep saying dereference on the slide, whatever. I choose to follow the pointer using that same operator. Find what was in memory at C's location, because C is a variable that stores an address, and update memory, the mailbox, the treasure map, whatever you want to call it, at that location with the value of 3. What is A now going to be when I print it? Yeah, it's a little bit of voodoo, right? This looks creepy, but it works. Because ultimately, A the variable, is just an abstraction for some location in memory. It's a very convenient abstraction. It's what we've been using all semester. A is just some 4-byte blob of memory at that particular location. That is all A is. We use this int keyword because it makes our life a lot easier to kind of not have to think about addresses generally, to instead just think about variables and what values they hold. But that's all A is at the end of the day. It's 4 bytes in the memory that the compiler put there for us. Every time we use A, we're either reading or writing those 4 bytes in memory. C was set up in this example to be a pointer. C is an address in memory as a variable type. We set C to be equal to the address of A. We did that explicitly in this example. You can ignore that malloc example. We'll play around with that later. C was set to be the address of A. When we actually printed that out, it was in the same exact location that A was located. It was pointing to the same location where A actually was. So when we actually followed the pointer, that's what that star is doing here, update in memory whatever is at that location and set it to 3. Even though we don't touch anywhere else in our program, A, which is just those 4 bytes in that location, got updated. If I didn't have that syntax and just set C equals 3, that would be now setting C to like a hard-coded address of 3. That would be bad news, first off, but it wouldn't update A. C is no longer pointing to it. It's pretty unhappy about that because it's converting it from a pointer type to an integer type. I'm now following C. Tell me what's in that location memory and update it. Similarly, A equals, star C. You can also, anywhere you're expecting an integer, you can have a followed integer pointer, and that's perfectly valid as well. That'll still be 3 when we print that out. We're going to learn a lot more syntax. And as we get to pointer of a pointer of a pointer and all that, it gets a little wonky, I think, though. As you go back to this topic, review the video, look at slides, and start to do the lab eventually for this topic, I think if you have this, you're good to go. I truly believe that. Again, we usually don't print out the absolute values of our addresses. We usually don't care where the compiler chose to put something, as long as it got put somewhere. Sometimes as a debugging technique in here just to illustrate that these things are put somewhere. That's the only reason we printed out the pointer. But this part, C equals ampersand A and star C equals 3. C was set to be A's address wherever that happened to be. We don't care. We've followed the pointer. We've put something in the mailbox. We put 3 in the mailbox wherever A's mailbox was. That's updated A's value. If you've got that, you're good to go. That also gives us a hint as to how scanf kind of works, right? Now, scanf itself is kind of complicated, so as opposed to trying to kind of re-implement scanf, for any function that's going to update things via pointers, we can just use that same syntax here. So you can then use these pointer variables as just inputs or arguments to your function to then not really even return anything from the function, but just update multiple things in memory that give you the same effect as having returned multiple variables from that function. You're going to call a function, and it's going to update potentially one or multiple locations in memory based on this pointer syntax, and that can then correspond to multiple variables in the caller function being updated. It gives you the same result as having to return integer values from this function. This is why we weren't able to easily write a swap function before. This would have been our attempt. If I said, give me a function that swaps two variables, you would say, well, here's what we do. Int A and int B are our inputs. We have that temp, remember, int temp equals B equals A equals B, or A equals temp. We've had that kind of code pattern quite a bit when we're sorting arrays and things like that. That function looks correct, but it doesn't work, right? It swaps A and B, but the scope of A and B are only local to that function. So if I were to set up my problem with y equals 5, x equals 7, I print out x and y. I don't know why I did y first. Anyway, then I call that swap of x and y. After printing it out, let's just comment out these two examples for now. X and y are in fact not going to be swapped. X is 7. Again, I don't know why I did it that way. X is 7, y is 5. We call that swap function. It does a swap, and if I had printed out a and b inside this function, it would in fact be swapped. But there's no end result. We're just changing that function's memory. If you don't remember why it's the case, we should look back to like the memory space for each function, that's 2 topics back now, is local to that function. You're messing with memory that's given to that function and is gone once that function is done. I'll bring that slide back up, probably on Wednesday at this rate. That function conceptually is correct, but in C, logically it does not work for us, swap function. With pointers now we can do it. There's no requirement you call your pointers something pointer. A and B isn't a very good name either, so calling it A pointer and B pointer is a little bit better than calling it A and B, I guess. Syntactically, it's a little ugly. You'll get a handle on it pretty soon. The inputs are not two integers anymore, the inputs are two addresses. Two addresses that happen to point to integer values and have to be passed to it as if they point to integer values. Then conceptually, every time we actually want to do something with that location in memory, we have to update the pointer. We have to follow the pointer. So int temp is not b equal to b anymore. Int temp is now whatever was at that address, whatever was at that mailbox that was b was pointing to, that location in the mailbox. Likewise, the actual swap between a and b, we have to follow both those pointers. And then finally, temp itself was just an integer, star a pointer, we follow and update what was in the original a mailbox with that value of temp that we grabbed from b's mailbox. So two mailboxes and like a desk temp storing that temporary value, grab it, put it here, put this one over here, then put this one back in the original location. I think I did that backwards, but conceptually that's what's happening there. We store a temporary location, a temporary value, we then do a swap. I did that correctly. Then we take that temporary value and put it back in that other mailbox that we have there. That is what our pointers allow us to do. This function doesn't return anything, right? It has just blank return call here. It takes as input two pointers. Anytime you follow that pointer on the left-hand side of a assignment operator, it's going to update in memory whatever address you gave that function. So when we now call swap pointer, we don't give it x and y. That would give us some weird result. They would treat x and y as addresses, but they're not. We can pass it explicitly the address of x and the address of y, and by following the pointers, we've actually swapped x and y because we've replaced the two locations in memory with each other. So that first attempt that we still do doesn't change the value of x and y. Now when we've done so via pointers, we've actually updated, again, the variable here and a pointer, b pointer, and temp are still, this is where it's a little tricky, are still local variables to that function. They haven't become global variables or anything of that sort. They're still input variables to that function, but they happen to encode addresses. So because a pointer and b pointer encode addresses, even though any changes I make to a pointer and b pointer aren't reflected after the function call, it doesn't move x around, it doesn't move y around, but because I'm following those pointers, I'm changing something that actually has to correspond then to this memory that is x and y in the caller function. It allows you to break that kind of abstraction of each function kind of just doing its own thing. And while the actual implementation details in scanf are going to be a lot more thorny, because scanf can handle these kind of arbitrary format strings, and there's a lot of possibilities of what scanf has to support, effectively that's what scanf is doing as well. You pass it one or multiple addresses to scanf, it then updates those locations in memory with the variables that it reads in via that scanf format string, that thing that printf and scanf do. And that's what I was trying to get at here in terms of visualizing the scope of a memory. We still have mains memory, we still have swaps memory. They're in different locations in memory. This idea of actually updating things only works because of the actual value we have stored in swaps memory. You can think of it and draw it as an arrow, and if you draw it out, you will help yourself debug your code that you're working on. It's storing that location. It's literally storing 0 and 4, or whatever large value that would be in our real world scenario. And we're still just messing with swaps local memory, but by following the pointer, we're actually then updating mains memory as kind of a side effect or like a byproduct. Since every variable is ultimately just an address in memory, pointers can get us around that restriction. The issue and why pointers can be seen as hard, there's a couple reasons. If I accidentally pass in 0 for a pointer. And you may say, I would never do, why would I ever pass 0 for, well, we do all sorts of things, right? We have a pointer that we wanted to initialize and we forgot to initialize it. You're right, you would never do 0. But let's say we had int star c, and I pass c. C is a pointer. It's not going to give you any warning or compile errors. What is this code going to do? It's going to crash. And you haven't had to deal with a lot of program crashes, maybe a couple. This is the most common cause of like runtime crashes, red text, core dump, segmentation fault. Here it says illegal instruction. I actually don't know what that means, to be honest. But a core dump is usually a side effect of a program crashing, and the most common cause for your programs crashing versus just returning the wrong result or getting stuck is accessing a value in memory, a location in memory that you don't have access to. You have the treasure map, but it's pointing to some property you're not allowed to go to because each program is given its own region or its own mailbox. You're using your key to try to unlock somebody else's mailbox. That is going to cause your program to crash every time. And you may say to yourself, that's never going to happen to me. It's going to happen a lot to you because as we start to work with pointers, there are a few things you have to kind of keep track in your head as you go. Don't be scared when that happens. You get red text, you get the term core dumped, you have a pointer problem. That's a huge hint. That tells you where your problem is. You can kind of figure out, all right, first one worked, second one worked, third one never worked. It crashed before it printed out the third thing. Something is wrong with my pointers either in the function or the caller of that function. It's a pretty strong hint, where your problem is in your program. Let's leave things here for today. Don't forget Wednesday's quiz. Good luck finishing up the lab, and I'll see everyone either in office hours today or on Wednesday.